Stop growing up for goodness sake. Throw your computer in a lake. I just want to live like a baby.
In this last video of this lecture, I want to discuss two more kinds of examples about spanning sets of modules. And these are examples that come from free modules and f bracket x modules. So first, let's say R is a ring with 1, and let M be the free module of rank n over R. So this is something we discussed in our first lecture on modules. This is on page 338 of Dumbin and Foote. We'll come back and talk much more about free modules in general in the next lecture. OK, so what does this look like? M is the set of all A1, A2 up through AN, where each AI is in the ring R. We can take these elements of M that look like standard basis vectors in Rn or in any vector space. So E1, 1, 0, 0, 0, E2, 0, 1, 0, 0, 0, 0, up to En, 0, 0, 0, 0, 1. So now we take any element of M, say the one that is S1, S2 up through Sn, where now each of these SIs is going to be some element of our ring. Well, this element is a finite linear combination, a finite R linear combination of these E1, E2 up through En. It's the sum from I equals 1 to n of Si times Ei, where this is the action of the ring element Si on the standard basis vector Ei. So what are we seeing? We can write anything in M as an R linear combination of these n elements. So M is generated by this set, E1 up through En. In the case that M is commutative, this is a minimal generating set. There's no generating set of size n minus 1 or smaller. There's something to prove there, but hopefully you believe it. And if R is not commutative, things can be a lot more complicated. So I don't want to talk about this in lecture, but I'll point you to two exercises, 24 and 27 of section 10.3, that show how this setup can be a lot more complicated when your ring is not commutative. Now I want to give a related example from Conrad's notes. Let's take R infinity to be the collection of all infinite length vectors, A1, A2, A3, and so on, one component for each positive integer, where each AI is in our ring. You can give this component-wise multiplication, and you can define an action of R by having the ring R act on each component individually. So it's got component-wise action of R. So that turns this R infinity into an R module. Let's take E1, E2, E3, and so on. Now, infinitely many of these things that have a 1 in exactly one position and 0 everywhere else. Now, let's note that this infinite set of these EIs is not a spanning set for this R infinity. Why not? Because to be a spanning set, we're taking finite R linear combinations of these elements. And if you just take finitely many of these EIs and act by elements of the ring, then any finite R linear combination of them is going to have all of the coordinates being 0 after some point. If you take finitely many, you've taken one largest one. So that means in all of the finitely many EIs that you've taken, there are all zeros past a certain point. And when you take the action of R on these EIs, that's not going to change which coordinates are non-zero. I mean, it's not going to take coordinates that were 0 and turn them into something non-zero, certainly. So any finite R linear combination of these has all the coordinates equal to 0 after some point. But R infinity has lots of elements that don't have that property. For example, if you take the element of R infinity that's just 1, 1, 1, 1, 1, 1, 1 for every component, there's no point past which you're getting all zeros. So what are we seeing? We're seeing that this infinite set is not a spanning set. This is the most natural guess you might first make for what a generating set for this module might look like. And now this is something to prove, but I'll say that R infinity also has no finite generating set. So it certainly has a generating set. Like we've already seen that every module has a generating set. You could just take every element of the module, but it has no finite generating set. This most natural infinite generating set that you would take doesn't actually work. It's not really a spanning set. So there's some question about like, what does a reasonable generating set for this thing look like? And I will leave that for now. An F module V, that is a vector space over the field F, is cyclic if and only if there exists a vector in your vector space such that the whole vector space is F times V. It's the set of all things of the form alpha times V, where alpha goes through the elements of your field. So we'll talk much more about vector spaces and things like dimension several lectures from now. But this means that V has to be a one-dimensional vector space over F, that everything in the vector space can be written as a scalar times one vector, little v. OK, so what about an F bracket X module V? So what is that? What's the difference? Well, now V still is a vector space over F, but an F bracket X module carries this additional structure of an action of X on the vector space, which has to be a linear transformation from V to itself. So if we fix one vector V, we have X times V is T of V, and X squared times V is T squared of V, T following T of V, and so on. X to the n times V is T to the n of V. So when is V a cyclic F bracket X module? Well, V is cyclic if and only if there's some vector in your vector space such that V is equal to f of x times v. So it's the set of all things of the form some polynomial times v. But what are polynomials? They're finite f linear combinations of powers of x. So you have this infinite set of vectors, v, x times v, x squared times v, x to the n times v, and so on, arbitrarily large powers. That gives vectors v, t of v, t squared of v, and so on. And if the finite f linear combinations of this set of vectors spans v, that means that you're a cyclic f bracket x module. But that's the same thing as saying that this set of vectors spans v as a vector space. So start with v, apply t to it, apply it again, apply it again. You get some set of vectors. If that spans v as a vector space, then v is a cyclic f bracket x module. OK, so when does that actually happen? Well, we can make some choices for different vector spaces v and linear transformations and see what happens. For example, if v is your vector space and t is the identity linear transformation, then what is this set of vectors? Well, it's v, t of v is v, t squared of v is v. It's just this single vector v. So the only way for v to be a cyclic f bracket x module when the linear transformation is the identity is if this vector space v is spanned by the single vector little v, which we said means that v is a one-dimensional vector space over f. Let's take another example where v is affine n space over the field f. So this is something that we talked about in our second lecture on modules. This was the, or I guess even the first lecture on modules. This is one of the first examples we talked about. Let's take t to be the shift operator. So this example we already talked about. So when we talked about f bracket x modules, we talked about this example quite a bit. So how does that shift operator work? Well, we take the standard basis vectors e1 up through en for affine n space. And how does the shift operator act on en? Well, t of en is en minus 1, and t squared of en is en minus 2. T to the k of en is en minus k if k is less than n, and it's 0 otherwise. All of the coordinates shift over by one position when you apply t, and then you pick up a 0 in the last coordinate. All right, so you can check that v is spanned by en. T of en is en minus 1. T squared of en is en minus 2. You keep going in this way, and you'll get en minus 1 down to e2, e1. And V really is spanned by those standard basis vectors. So that means that V is a cyclic f bracket x module with generator En. So let me just note, V is not a cyclic f module. It's a cyclic f bracket x module with generator En, but it's not a cyclic f module when n is bigger than 1. Why not? Well, the last thing we need is that this affine n space is a vector space of dimension more than 1. In fact, it is a vector space of dimension n, and we'll talk about that all more later. All right, so this sort of brings up a question, which is, if you're given an f bracket x module, how do you tell whether it's cyclic? Is there a nice characterization of the ones that are cyclic? And we'll come back and talk about that more later.